All right, so we have one last lesson in this first chapter to go here. It's Scatterplots is the name of the game today. This is going to feel a little bit different than what we've done in the last couple of days, but at the same time, it's also going to connect all the different things that we've covered in the last couple of days. Now, I will note the last two lessons we've had, they've been very long, and I apologize. You know, over 30 minutes certainly isn't ideal. I'm hoping that today won't be as long. I mean, if you're watching this right now, you can just see how long the video is. You'll know if I'm a liar or not. But man, I hope I don't eat my words on that. Let's see how we can get this done. So, like I said, we're going to look at something a bit different today, something called scatter plots. These are where you have lots of data on a graph that doesn't exactly follow a perfect pattern. In other words, it doesn't perfectly follow a line. However, it does have a general trend to it. So we'll talk about how we can make that work. Three main ideas that we're going to deal with today before we really get at this. We'll talk about lines of best fit, which is definitely the most important thing we'll talk about today. We'll talk about correlation strength, and we'll also talk about outliers. Like I mentioned at the start here, this is the last topic of the first chapter, so we're done after this. The way I outline this course, remember, is we have a chapter assignment that I'm going to give you after this, but then you'll also have an exam that you'll have to write as well. And I do those on Chromebooks. But again, if you're just someone else who's watching this, you don't worry about that. Here's a lesson. So first of all, get right to it, a scatter plot. When data is collected, sometimes or oftentimes it doesn't follow a perfectly predictable pattern. In other words, it doesn't always line up exactly on a perfect line. So the data can look scattered if you plot it on a graph, hence the name scatter plot. However, even with these variations between data points, like you're seeing in those two pictures there, a linear relation can still be approximated from the data if the points tend to increase or decrease in a more or less linear fashion. Now, both of these pictures here, there is kind of a trend to it. Now, this one on the left is certainly a lot stronger, hence name a stronger positive linear association. But you definitely can see that it kind of follows a trend going upwards. It's not a perfectly straight line, but you could approximate a perfect straight line through that, which we'll get to in a moment. Now, the one on the right also has a general trend to it. It's just not as strong as the other one because they're kind of still all scattered out. But if you were to draw a line there, you would see that it would look something like that. So there more or less is a trend to it. It still is increasing. It's just kind of all over the place. Now, this whole idea of drawing a line in there, that's actually one of the next things, if not the next thing. Yep, it is the next thing we're talking about. You can approximate a linear relation on a scatter plot by using something called a line of best fit. Basically, this is just a line that can be drawn to equally split your data points above and below that line. Now, I'm going to kind of just stop here for a second and let you know that drawing a line of best fit is not an exact science. At least I would argue it's not an exact science. It's more of an eyeball and a good, solid estimate, right? So if you really look at the data that you have and you try to split it as evenly as you possibly can, chances are you're going to make a pretty good line of best fit. But two different people could draw slightly different lines of best fit, just so we're aware. Now, ideally, you wouldn't. But just so you're aware, this is not an exact science. It's certainly not Math 30-3. Now, once you have a line of best fit, you can use it to calculate a slope, which is m in a linear equation. So once you have this line of best fit drawn, just basically pretend you don't have a scatter plot at all. You can find your slope, your rise over your run, and you can go to town on it like you usually would, right? Also, if you extend the line to the y-axis, this line is a perfect example of extending it. If you try to extend it as best you can, it'd be way easier with a ruler. But if you try to extend it the best you can and you make it all the way to your y-axis, just remember that your y-intercept is your value of b. So if you find your rise over run of just your line of best fit, so rise over run of just your line of best fit, that tells you your m. And then if you extend your line to your y-axis, that tells you your b. And then bingo, bango, bongo, we have y equals mx plus b. Awesome, right? So scatter plots are not really anything super different. The whole idea here is you have to be able to draw a line of best fit by approximating it with the data that you have. Now, there's a few other things we have to talk about before we really start working with this, and that's correlation, first of all. So correlation, also known as association, is just basically how tightly packed your data is. So just like we looked at with those pictures earlier, if you have data that's really tightly packed together, we have strong correlation. So this one here, I would say, is relatively strong positive correlation. It's positive because it is going up. It has a positive slope. This one is also similar. The data is pretty closely packed together, but it's going downwards. That is negative association or negative correlation. And I would also argue that that one is strong. Now, weak correlation would be like the one a little while ago right here, where things are a lot more scattered apart and not quite as close to what that line of best fit would be. That's what we would call weak correlation or weak association if you prefer. Now, it's also important to note that you don't always have linear association. We can't draw a real line of best fit with these. If you see this one, you can clearly see these dots kind of make a U shape. You could pretend that you can draw a line of best fit and say, oh, look at this. I've put half of them above and half of them below. You haven't really done anything though, because clearly the data follows a trend that looks like this, but the line of best fit isn't linear in that case. So it's not truthfully a good one to deal with. So we won't be dealing with anything like that. And then same with this one, there's not really any association here. You could draw a line of best fit like this and be like, hey, look at that, I divided it. But you could also do something like this and be like, hey, I divided it. You could even do something like this, or you could do something like this. Yeah, it wouldn't really work, right? So something like this has no association or no correlation at all. It's not even weak, it's just no correlation at all. We are not interested in ones like that. We're interested in ones like this one or ones like this one. Those are the ones where we can actually get a linear relation out of them by drawing an actual good, accurate line of best fit. Hopefully that makes some sense. Now, the last little, vocabulary thing we have to deal with is something called an outlier, which is, I think, exactly what it sounds like. An outlier is just a piece of data that lies out of where the rest of them would be. Now, generally speaking, when we have outliers, we can just ignore them as part of the data set. So if you can see a line of best fit, like in this one, we could probably draw a line of best fit, something like this. Maybe that one's not even great. Maybe something more like this. There we go. That's probably a little more accurate. When you draw a line of best fit, but you're like, hey, what's going on with this one? This one's way out here. If there's only a couple that are way out there, and even like these ones down here, you can just kind of ignore them, right? Now, in the context of this image that I put here, kind of an interesting one, more of like a social studies thing than anything. This graph is showing life expectancy versus healthcare expenditure. So in other words, how much governments are spending on healthcare per capita. So in other words, per person. And what you can tell in a graph like this is the more money, generally speaking, that a government spends on healthcare, generally speaking, the longer people are going to live, or vice versa. The longer people are going to live, the more money was spent on healthcare. Now, there are some outliers, like you see Latvia, for instance, spends, it says 20 on healthcare. But even other countries that spend a similar amount, like Chile or Poland, are experiencing a much higher life expectancy. So there might be some other factors or other meanings behind that. Of course, the biggest outlier on here, as we can see, is the United States. They spend by far the most on healthcare, but they don't have the highest, life expectancy. Maybe there's some reasons behind that. Maybe, who knows, right? Let you extrapolate what you want from that. I just found this as a good example of an outlier. That's all. But anyway, moving on. So back to actual math stuff today. We're going to blitz through these questions. Draw a scatter plot of the following data. Now, drawing scatter plots, I'm not going to lie, I find them a big pain. I find this really annoying. It's just like really tedious, but we don't really have a choice. What I do when I look at a data plot, a scatter plot, is I look at my data and I try to find in my X direction my smallest value and my largest value. Well, my smallest one is here and my largest one is here. Now, the reason I care about that is I want to figure out how to make a scale along my x-axis. So I see I'm going from 0.75 up to a maximum of 6. So I know what my scale is going to have to kind of be there, right? Now I do the exact same thing with y. Look at the smallest one on my y-axis. It looks like this one is my smallest one here. And then my largest one looks like it's this one here. So I'm going from 0.5 to 5.55. So I'm going to make my plot. I know I'm not dealing with any negative numbers, so I have no issue making my plot like so. Well, that was miserable. Hold on, let me do better there. Hold on. Here we go. Fingers crossed that this works a little bit better. Not overly, but it is what it is. It is what it is. It's really tough drawing a straight line on this tablet thing that I've got. Anyway, so that's my y-axis. I'll do an x-axis along this way. There we go. Good. Now I know in my x direction, I'm going from about 0 to about 6. So why don't I make every second block 1? So I'll say this is 1. There we go. This is 2. This is 3, 4, 5, and 6. And then likewise in my y direction, I'm going from 0.5 to 5.5. So I think I'll do the exact same scale. I'll say this is 1, this is 2, This is 3, 4, 5, and 6. It's really important that you define your scale for what you need. And this is just a skill that you have to build on your own as time goes on. But the easiest way to do that, again, like I just showed you, is find your smallest and your largest in both your X and your Y. That kind of sets the range by which you're working, right? Now, here's where the busy work comes in. Now that we got our graph set up, now we actually have to plot the data. Just for fun, I'm going to change color here. I'll make this blue. So the first point is 6, 5. Okay, so 6, 5, there's a point right there. I'm going to check them off as I go. So that one's done. Next one, 5, 3, 5, 3. There we go. That one's done. Like I said, this is just tedious, but it is what it is. Next one, 2.5, 3.5. So 2.5, 3.5, that's right here. There we go. Good. Next one, 0.75 and then 0.5. That would be right there. Good. Done. What about 3.1? 3.1 is right there. Good. 5.5. That's right here. And then 3.25. That is right there. Pretty close to that other one we put on there. That's interesting. What about this one? 4, 5.5. 4, 5.5. That's way up here. Good. And then 2.2. That one was easy, 2.2, and then 4, 3.5. Finally, we're almost done. There we go, 4, 3.5. There it is. Whew, okay, so we got that scatter plot down. We got all those things are on there. So now here's some questions to go with that. In that previous example, was it linear or nonlinear? And if it was linear, was it direct or partial? Just a reminder what that means. Direct means it goes through 0, 0, and partial means it doesn't. Let's have a look at it again. First of all, can we see a linear trend to this? Well, there's sort of a linear trend to this. It certainly isn't super clear. I'm going to change pen color one more time here. You can kind of tell that as your X goes up, your Y generally goes up as well, but it's not really tightly packed together. So in other words, I'd call this a pretty weak correlation. But in terms as to whether or not this is linear, I feel pretty safe to say that, yeah, this is linear. You could draw a line of best fit kind of like this, I'd say. That would be my line of best fit, where half of them are above and half of them are below. So I would say, yeah, this is linear. So I'd say linear. But was it direct or partial? Direct, again, means it goes through 0, 0. I don't see a way of really reasonably drawing a line of best fit through 0, 0. You know, you could maybe, like if you really angled it over this way. I'm just trying even to visualize. I'm going to say like, no, I would say it's partial, if anything. You might disagree. Some people might say that's direct, depending on how you drew your line of best fit. That's really where it comes down to. But I guess it's a good discussion point because when you have a line of best fit, really getting to discussion as to whether it's direct or partial, that really is a matter of opinion. It depends on how you drew your line of best fit. But personally, I would say no. I'm sure someone could argue otherwise. Next one, what is the direction of the correlation? Is it positive or negative, if any? So when we talk about direction of correlation, a positive correlation is where it's going up as time goes on, or as X goes on, I should say. And a negative is where it's going down. I think this one's pretty clear. This is certainly a positive correlation. There certainly is some correlation here. It's just not very strong. And that brings us into the third point. What is the strength of the correlation? Look how far apart everything is from that line of best fit. There's not really much that goes through it. Like this point seemed pretty good, but all these others are pretty far away from it. I would say this is pretty weak correlation. And then last, are there any outliers? I mean, it depends on how loose you want to say an outlier here. I would say there's a lot of outliers, or there's just none at all. Just to save us time, I'm going to say not really. Not really. I wouldn't say there's any real outliers, but there is weak correlation, which makes most of those kind of look like outliers. Now, I would say there was an outlier if all of a sudden we had a point. I'll just draw it in here. If we had a point like right here, that would definitely be an outlier, because that'd be like, whoa, that's about as high as we get, but it's pretty low on our X scale. I'm not seeing anything quite that extreme sticking out. So that's why I'm kind of leaning more towards saying not really. Anyway, that was quite a bulky question. We got a few more that'll be hopefully a little bit more clear. Create an equation for this scatter plot. Now this is kind of tricky because an equation must be in the form y equals mx plus b. We need to get a good line of best fit going here. Now, I'm going to be honest. Questions like this are really up to your own perspective. When I talk about drawing a line of best fit, there is no perfectly right or perfectly wrong answer. Well, you know what? Never mind. There is actually, if you drew a line of best fit that was like this, I'm sorry, that's a perfectly wrong answer. A line of best fit, though, just divides your data points 50-50, half of them above, half of them below. If you can try to strike through as many as you can, that's ideal. But generally speaking, half of them will be above and half of them will be below. If I'm looking at this, if I'm just trying to angle how I would do this, I think probably the best way would be to start somewhere along here and kind of angle it through this. So if I kind of just take a couple passes at this, maybe I'll try this first. Maybe I'll draw a line of best fit like this. And that actually, I think, is pretty much right on, because notice I have 4 points directly above, 2 points that are right on the line, and then 4 points below. I would say that's a pretty awesome line of best fit right there. But again, if I didn't get it right the first time, I would have just erased it and I would have tried again. Not the end of the world. Now, in terms of getting an equation, we need an mx plus b. Let's start with a b value. B is where we cross our y-axis. It's our y-intercept, right? I'm going to have to just estimate this here, as you will with any scatter plot. You just have to estimate this. I'm going to estimate that at about 0.75. So I'm going to say b is about 0.75. Now, as for m, really, that's our rise over our run. How about I just change color again? Really, I want to pick whatever points I feel most comfortable in. I'm just going to start with this point right here, because I know that's at 0, and then 0.75 is what I'm estimating it at. And I'm going to assume I went right through this point right here, which is at 8.4. So if I'm talking about my rise, that's my rise. I went from 0.75 up to 4. Well, if it was 1 to 4, that'd be an increase of 3, but then I actually started at 0.75. So I would say my rise is 3.25, and my run is from 0 to 8. Well, that's a much more obvious number. That's just going to be 8. So in terms of a rise over a run, I would say my rise over run is 3.25 over 8. That's probably not going to be a nice decimal, but let's see. 3.25 divided by 8. Yeah, it's pretty bad. So you know what? I'm going to just round it to the nearest hundredth. I'm going to say that's about 0.41. That'll be my m value, right? Again, I can't stress this enough. When you're making an equation for a scatter plot, it's just an estimate. Just do your best with a line of best fit, and that's going to be good enough. As long as there's some logical sense to it, it's fine. It's not the end of the world. So anyway, I know what my m is. I know what my b is. So therefore, we know y equals 0.41x plus 0.75. Pretty horrible looking, but that's the way it goes with scatter plots. Scatter plots are by no means perfect. You just make a line of best fit and you hope for the best. Last question, I think. Yes, last question. Here we go. Create an equation for this scatter plot. So just like before, we want to make a decent line of best fit. All right, here we go. So again, try to divide these points as best you can. I think I'm going to start about right here and draw my line kind of like that. And hey, you know what? Once again, that looks not too bad. I mean, I have 4 that are above, and it looks like 3 for sure that are below. Well, I mean, this one's kind of below as well. I would say that's probably good enough. And you know what's nice about this one? Notice where I'm starting. We're going to use that in just a second. So an equation for the scatter plot, y equals mx plus b. Once again, I always start with b. That's what I was alluding to just a second ago. B is your y-intercept. Looks like b is exactly 22 in this case. So that was nice starting there. You could have started somewhere else. That's okay. Nothing wrong with that. Got to make that very clear. Now the next thing we need is m. M is our rise over our run. Try to find some points that are pretty clear. This point right here looks pretty clear, and I think I went right through it. So let's find our rise there. So we're actually going down. So we went from 22 down to this point, which is 14. So we went from 22 to 14. That means we went down by 8. So our rise is -8. And our run is we went from 0 all the way over here to 22. So our run was 22. So m is -8 over 22. Once again, throw that in your calculator. Oh, that's a pretty messy decimal. Once again, I'm going to round to the nearest hundredth, I guess. I mean, you could also leave it as a fraction. There's nothing wrong with that. If you want to leave it as a fraction, at least that way it's accurate. But whatever, I'll write it as a decimal. Rounding this to the nearest hundredth as a decimal, it's 0.36. So I can write this now. Y equals mx plus b. We know m. Oh, sorry, -0.36. My mistake. Anyway, y equals negative 0.36x plus b. B is 22. There it is. Again, I know I'm going to sound like a broken record here. These look terrible. They always will. Line of best fit, it's not perfect, right? Two different people could draw two different lines of best fit. If someone were to ever tell you that there is a perfect exact answer for this, I mean, they might have a point, there might be, but there's nothing perfect in this course. In Math 30-3, do not worry about being perfect on this one. We just want you to have the right idea. That's it, okay? Start with your line of best fit. Do your best. As long as it's a decent looking line of best fit, you're fine. I do not mind. Anyway, look at that. I was right. We're only about 20 minutes into this. For practice, you can work on your handout that's in your booklet. We are officially done chapter number 1 and in a much shorter video than before. If you have any questions, though, make sure you are asking for help, and I will be more than happy to help you. Best of luck.